All right, so for tonight, we're taking a look at P3, polynomials and special products. So I need everybody to turn into their books on page 26. So polynomials are math expressions that have terms with variables and real numbers. Couple things to remember. You're going to see the term or the phrasing standard form. All right, that's when the polynomial is written in decreasing exponential order. So for example, x squared plus 5x minus 7 is in standard form. The degree, okay, another vocab word, it's the highest exponent in the expression. The lead coefficient is going to be the number in front of the variable with the highest exponent. All right, so there's a section coming up, I believe, in your homework where they're going to be asking you to identify these things. So hopefully these definitions will help you with that. Example number 1 goes through those as well. So if you need to or want to, go through A, B, and C. Okay. There's also another checkpoint question there for you to go through if you need a little bit more. Now, when adding and subtracting polynomials, you can only combine terms that have identical powers of variables. So for example, an x term can be added or subtracted to another x term. An x squared term can be added or subtracted with another x squared term, and so on and so on. But you cannot mix them. So simply having x's doesn't mean that they can be combined. The power has to match as well. Okay? Take a look at example number 2 on page 27. The first one is an addition one, problem 2a. So you can see where there's some x to the third power terms that were combined, some x squared problems that went together. Notice that the first polynomial did not have a plain x term, so the negative x in the second one did not have anything to get combined with, so it's still just there by itself. And then there were two constants in them as well, so the negative and the 3 went to, or negative 3 and the 8 went together and made the 5. Okay, now B. Let's everybody take a look at B with me. This is a subtraction one. And not that it's overly hard, but kids do make some mistakes with this one. When you subtract that second polynomial from the first, every term is subtracted from the first polynomial. All right, so kids do real well with the lead one. You know, the 7x to the fourth minus 3x to the fourth. That usually doesn't get messed up. But now when you're combining the x squared ones, you've got negative x squared in the first. Subtract a negative 4x squared in the second. That's negative x squared minus a minus 4x squared. What happens, you guys, when you do subtract a negative minus a minus? It turns to positive, right? So you actually end up with negative x squared plus 4x squared. All right, so in the end answer, you can see that positive 3x squared results from that. And again, when you're doing the x terms, you got negative 4x in the first, subtract 3x in the next. That's negative 7x total. And then there was a constant in the first one, a 2, and nothing to take from it in the second one, so you still have a 2 in your answer. So watch that. Now, often, I have suggested to kids to distribute the negative through that second parenthesis and turn it into an addition problem. Okay, so that's another strategy that you can do. If you wanted to start in that problem and go adding a negative 3x to the fourth, positive 4x squared, minus 3x, that might not be a bad idea. Okay, so just be careful on the subtraction ones. They're not difficult, they're just a little bit trickier, and sometimes people make a mistake because they don't subtract each term. Multiplying polynomials. Now the nice thing with multiplying in algebra is anything can be multiplied together. Make sure that you're still thinking about your rules of exponents that we reviewed in our last section. Okay, but when you have polynomial times polynomial, everything in the first expression has to be multiplied by everything in the second expression. Now you played around with this whole thought using FOIL in the past, where you had a binomial times a binomial, a two-parter times another two-parter, and we did the FOIL. Okay, hopefully everybody remembers FOIL. I think you used it enough. On the next screen, we're going to go through a review of that. So if we were going to multiply these two binomials, 3x minus 1 by 2x plus 5, okay, the first terms would be 3x times 2x, and we get 6x squared. The outsides would be 3x times 5, we get a positive 15x. Inside is negative 1 times 2x, we get negative 2x. And then the last terms of each would be the negative 1 times the 5 for a negative 5. Now when we FOIL, generally there's going to be some matches that we can condense and reduce for our final answer. So notice that the 15x and the negative 2x match. They can be combined to the 13x and we get our end answer, 6x squared plus 13x minus 5. Turn to page 28. Page 28 gives us another way to multiply, and it's by vertically stacking the problem, kind of like you do with whole numbers when you're doing a multiplication. And it essentially it works in the same way too. And it's just a way to organize it to make sure that you do that distribution of each term to each term in the second one, rather than just doing, a few of them and missing something. So I'm going to go through one of these with you. So on the next screen, most of this screen doesn't need to be written down, so I'm going to pop to the next one right away. And we're going to take a look at this one together. Okay, so let's see. I bet my screen's going to pop forward if I try to write on my board. Let's give this a try. All right, so my first one is x squared plus 3x minus 5, and I want to multiply it by x squared minus 2x plus 1. So now in the past, you've started with the 1 in the second row and worked it through the top. When you're dealing with polynomials, you actually are going to start from the left. And the reason that we do that, like I was mentioning on that prior slide, it's going to keep your exponents in descending order. Okay, so I'm actually going to start with the x squared, and I'm going to multiply it by the top row. So x squared times x squared is x to the 4th. X squared times 3x is positive 3x to the 3rd. X squared times negative 5 is negative 5x squared. So you sent the x squared through the entire top row. You're done with that one. Move on now to the negative 2x. Now, just like used to move into the left one spot, we're going to move over to the right one spot. As we take negative 2x times x squared, you're going to get negative 2x cubed. Negative 2x times 3x is negative 6x squared. And negative 2x times negative 5 is positive 10x. And now we have finished using the negative 2x term. Move on to the 1. Slide over another spot. 1 times x squared is x squared. 1 times 3x is positive 3x. And 1 times negative 5 is negative 5. Now all of your terms are lined up, and you can go ahead and combine them just like you would in traditional multiplication with all numbers. So we've got an x to the 4th out front plus x cubed. We have negative 5, negative 6, and positive 1. So we have a negative 10x squared. Then you've got 10x and 3x, which makes 13x. And then the negative 5 constant is all by itself. Okay. Again, you don't have to do it that way. You can leave them side by side and just send them, as they're sitting there. But stacking them is kind of a clever way to help with that. All right. We're going to be looking at some polynomials that are a little bit more special. And if you can recognize the patterns in them, the multiplying of them, or the working with them, or down the road, the factoring of them is a lot faster. So look at the bottom box of page 28, and please put them into your notes. Okay, so we have special products in that box. If you have u plus v times u minus v, remember that difference of perfect squares? You'd end up with u squared minus v squared as an answer. They do give you one that is done with numbers and stuff, a little bit easier to understand off to the side. So take a look at the example there. We've got the square of a binomial. So if you had something like x plus 3 times another x plus 3, what does it end up looking like? Same thing with a subtraction rather than addition in that binomial. Okay, cubes of binomials are at the bottom. Okay, just give you a couple of seconds to look through those. Okay, now if you don't remember these patterns, there is nothing saying that you can't list these things out and multiply them through FOILing and using multiplication methods. It's just a time-saving thing if you can remember the patterns. Okay. Now, examples 5 through 7 on the following page have you playing around with these. So look through them. Again, notice there are checkpoints for each of them. If you want to do one independently on your own and check yourself online, that would be awesome. Now, example number 8 at the bottom of page 29. Take a look at that. You have x plus y minus 2 and x plus y plus 2. They're almost identical outside of the negative 2 and the positive 2 in both of them. All right, so take a look what they did here. What they did was they grouped. Okay, remember you can do that grouping thing. And it turned it into a difference of same term binomials, just like the previous page. You've got an x plus y minus 2 and an x plus y plus 2. And now you can put that pattern to it. It's going to be x plus y squared minus 2 times 2. Okay, so again, you can play around with that. I don't know that I would always notice it, to tell you the truth. If I was looking at a problem like that, I would probably just multiply the trinomial times trinomial and get my end answer. It's if you notice those patterns again, it can be a time-saving piece because it's not that hard to do x plus y times x plus y, and obviously it's not very hard to do negative 2 times positive 2. So, if you catch stuff like that and can play around with it, it can be a time-saving thing. Not a life or death thing, but maybe time-saving. All right, turn the page to question or example number 9 on page 30. They've got a word problem application for us here that deals with the volume of a box. Now, the algebra piece to the volume of a box is they didn't give us the dimensions. They didn't give us the length, the width, the height. They tell us about them. It says an open box is made by cutting squares from the corners of a piece of metal that is 16 inches by 20 as shown in the figure. The edge is cut out x inches. Okay, so the edges are x long. So if the cardboard was 20 the long way, and you cut in x from one side and from the other, the actual length that the box is going to end up being is 20 minus 2x, right? Okay, it tells us that the width was 16. All right, but again, you're making those cuts in to fold up the box. So you're coming in x from both sides, and that width ends up being 16 minus 2x then. So if you folded this up, then how tall would your box be? Okay, well, think of those flaps that you just cut. That's going to be the height of your box. So the height of the box is going to be x. And you can see the box folded up underneath that first drawing. It has 20 minus 2x for the length, 16 minus 2x for the width, and x for the height. Now you guys should all be able to remember how to find the volume of a box. It's length times width times height, so you have to take those expressions then and multiply them together. All right, so you can see the expression they get for volume there underneath the solution, 320x minus 72x squared plus 4x cubed. So if they had you play around with the height of the box being 1 or the height of the box being 2 or 3, you can see how they have changed that initial height, which would therefore change your width and your length, and you can see what it does to your volume. So as they're making the box taller, it's actually making the volume of the box grow. Okay, so it's just one of those application things to get you thinking about, well, if you did this, what would happen? All right, so in this case, if you made it taller, so in other words, if you cut in further, it would end up making the volume more. So the taller this box grew, the more volume it ends up having. All right, so that's just a trial and error experiment kind of thing. Get you thinking. All right, kids, that one was a shorter one than the day before. So we're going to cut you loose on the homework. Don't freak out when you see how many problems are in this section. It does go from 1 to 103, but again, we're going to cut it back. Okay, so we're going to do every third starting with problem number 3. Okay, actually you can start with problem number 6. I take that back. So start with problem number 6. Do every third one. It's going to end up being about 30 problems or so. And if you've got the notes taken down and this watched at home, you've got all of class to do that. So give it a start tonight if you've got time. Otherwise, you can work on it some more in class tomorrow. All right, see you guys in class.